Thank you. Welcome to our talk, Dashboards and Dragons, Crafting SLOs to Tame AI Platform Chaos at Scale. My name's Alexa Griffith. As a hobby, I also have a podcast. It's called Alexa's Input, but my real job is I'm a senior software engineer. I work on AI platforms engineering at Bloomberg, specifically around building an inference platform.
And my name is Gavin Lee. I'm a senior software engineer, and I work in the same team with Alexa. So, yeah, welcome, brave adventurers, to our quest where we will craft the SLOs to vanquish the chaos hunting our AI realms. So let our quest begins. Let's check our treasure map for today's journey. We'll tackle the Gen AI Hydra, peer into the crystal ball of observability, venture deep into the dashboard dungeon, and defend against the fortress of platform challenges. All the artwork credits goes to Alexa. As you can tell, she had a lot of fun making them. Probably too much fun. First, a little bit about AI platforms at Bloomberg. We service the whole model development lifecycle, from data exploration all the way to model serving and maintenance. There are various platform teams and services within our AI platforms supporting the whole ecosystem. We offer a variety of services from Jupyter Notebook, managed inference, to AI pipeline tools. Now let's get into SLOs. Think of SLOs as an ancient runes, each holding the magic to illuminate the health of your platform. Decoding these runes gave us clarity in uncertain times. SLOs are made of 4 parts: SLI, service level indicator, objective, target value, and time window. Just like any magic potion, SLIs and SLOs combine carefully chosen ingredients. The common language between engineers, operations, and stakeholders. They are user-focused. They highlight real impact and prioritize improvements. They need to be a guidance to help us clearly navigate trade-offs in reliability, innovation, and velocity. However, not every quest has the same dangers. Similarly, each platform, training, inference, whether predictive or Gen AI, faces unique foes and require customized spells for maximum effectiveness. In this talk, we'll focus only on Gen AI platforms, which is what my team has been focusing on. Gen AI platforms typically have batch and interactive workloads, and it's usually a context-based and stateful. Therefore, the SLOs we care about are streaming latency, concurrency, availability, and so on. The Gen AI Hydra is tricky. Chop off one head, like inconsistent deployments, and 2 more heads pops up, like security and observability issues. We should arm ourselves wisely. So in multi-cluster hybrid platforms, we even have added complexity from these components and need to account for cross-cluster traffic and scaling across on-prem and cloud environments. This is an example high-level view of a Gen AI platform. We have a gateway that can route to both on-prem and cloud model providers. With that in mind, let's see an example of a request quest. Every request embarks on its own epic journey across the platform. A request could go through multiple hops within the gateway, like authorization, rate limiter, and such. Then it gets routed to a model provider. If it's a self-hosted model, it has to be pre-filled and decoded and so on. On each step, there can be latencies, there can be failures. As a platform team, we need to clearly understand and manage what is going on every one of these steps. Our intended metrics have clear hierarchies. Client-facing SLOs are crucial for SLAs. They define user experience standards, so we prioritize them differently based on whether they're user-facing, internal, or batch. We also need platform-level metrics, which tracks internal infrastructure health and guide scaling and resource planning. We need model-level metrics, which indicates the performance of models. They also they also need to indicate they need to tell us the reliability, latency, and cost efficiency. So what's in the spell book of metrics? What metrics are the most essential for Gen AI? For us, we care about reliability, we care about scalability, the number of tokens, not just requests our platform is processing, cost effectiveness, how well we're doing for optimizations like automatic routing, model caching, or prompt optimization and latency. As platform team, we're in a unique position. We're not just responsible for monitoring a single service, but the overall health of our platform itself. Now imagine a scenario. Resources across the platform are suddenly wiped out. Was it a scheduled cleanup job, a misconfigured script, a failure in the underlying infrastructure? Or let's take something more subtle. What if latency slowly creeps up across services? What if traffic goes completely quiet? The question becomes, how long would it take for us to notice? In too many cases, we find out when users complain. But by that point, it's already too late. The impact has happened. The frustration has already set in. We already lost some trust from the users. Without real-time visibility, platform teams are stuck in reactive mode. But with the right observability tools in place, they can detect anomalies early, respond effectively, and most importantly, contain the blast radius before it spreads. This is what modern platform observability is really about. Not just dashboards and alerts, but giving teams the power to stay ahead of problems and maintain confidence in the health of our system. Without our SLO dashboards, we wandered in darkness. Now our dashboards illuminate our path clearly.
So before we go any further, I just want to give a quick disclaimer that all of these dashboards used in this presentation are just for the purpose of the demonstration. They don't indicate anything about the actual state of any system in any organization. With that being said, now I can move forward. So let's talk about the way dashboards fail. So this slide addresses a problem many of us face, even with the best intentions, that dashboards often do fail to deliver us the clarity or value that they're meant to provide. First, a lot of times we have way too much noise and not enough signal. So take the example here on this slide. With everything layered together, it's nearly impossible to see what actually matters. Second, these dashboards are often rarely maintained. They get set up once, but as you modify, change in things like infrastructure or your business priorities evolve, they quickly become stale and just keep creating new ones maybe. So this could lead to misleading signals or outdated metrics. Third, we also run into siloed views oftentimes. So you might know that Model 2 has a higher latency, but you don't know why or whether it's affecting the user experience or if it really matters. There's just no connection to upstream traffic patterns, downstream failures, or what the business impact is. So finally, observability without action is just storage. Without defined thresholds or those SLOs we just talked about, without alerting on them, teams then won't be able to discern which metrics require immediate attention versus those that are okay and within acceptable limits. So just a big shout out to Sal Farino, who's a great person to go to at Bloomberg for everything reliability. He said, if a dashboard takes more than 90 seconds to understand, it's bad. So how are we going to create great dashboards? Step one is to start with the user. So you ask yourself, what does good look like from their point of view? Is it fast page loads, failed API calls? What will be our North Star? So next, you need to choose metrics that actually map to that experience. So latency, error rates, or throughput. You just need to be careful because just because a metric is able to be measured doesn't mean that it's meaningful. So you need to pick ones that align with actual performance outcomes. Third, you need to make sure that your infrastructure can support what you're trying to measure. If you cannot reliably collect the correct data that you need, or you're missing visibility in certain layers, then you won't be able to trust your SLIs when it matters when it matters most, sorry. So, but you need to start with what you have and then work in to fill in those missing pieces. So after that, you need to test your assumptions. To use real world baseline data from your system to validate that your chosen SLIs actually reflect the end user experience, and use this real world data to create your SLIs. So for existing systems, this is where the phrase look back to look forward really applies. And finally, you want to benchmark what's realistically achievable. You don't want to aim for 100% if your system has never even hit more than 99.5%. So you need your SLOs to be reasonable, and they should stretch your teams, but they should be still remain attainable. And that's how you can drive improvement to your systems without burnout. So let's look into the crystal ball of reliability. When you're designing effective observability dashboards, it starts with an at-a-glance clarity. The goal is to instantly be able to answer, is everything healthy? Is everything healthy? And if it's not, where should we look first? So we want simplicity at this level. You need to design with high cardinality in mind. So today's systems generate a lot of data with many dimensions. So dashboards should at least be capable of slicing and dicing this complexity without it becoming too overwhelming. It's important that you balance both of these, the aggregated global views and the ability to drill down. So you want a top level pulse, but also the flexibility to zoom into certain services, time ranges, or error types when there are certain issues arise. Dashboards are even more powerful when they're supplemented with contextual data, so traces and logs. It's not just about the metrics themselves, but the story behind them. So finally, the focus should always be on actionable insights, being able to take action on your dashboard. So prioritizing very clear thresholds, meaningful alerts, and have SLO driven triggers that help teams know when to act and what they need to act on. So let's start looking at some dashboards and evaluating them and see what we can find out. So in this dashboard, it's well structured into key performance areas. We see success rates, burn rates, error budgets, latency, and throughput. This dashboard gives us a 360-degree view of Model 1's performance with respect to its SLOs, request success, and inference latency over time. So starting with the good news, it seems that this model has had perfect success rates for the last hour, day, and even the past 7 days. So the short-term reliability is strong. However, looking at the 28-day window, the success rate does drop to 99.9%, which is just on the edge of our target. More importantly, the burn rate is 1.12, so we've exceeded our long-term error budget. Not by a lot, but we have exceeded it. You can see this is a slow increase in the burn rate over time chart. It's not a spike, but it's a climb. So this tells us that this isn't a one-time outage, but it's instead a pattern of small repeated failures. So looking at latency, we see a lot of fluctuation in TTFT, which is time to first token, and ITL, which is intertoken latency, also shows two clear spikes. And we'll get into what these mean in a couple slides. So these could be early signs of scaling inefficiencies or model bottlenecks under load. So while throughput is relatively low, we do see there's still error bars, not a major concern right now, but it is contributing to the budget burn. So overall, this model is doing well in the short term, but you're starting to see early signs of degradation over time. It's maybe a good candidate for some preventative optimization, whether that's maybe some retry logic, latency tuning, or adjusting how we're handling our edge cases. Let's look at uptime and success rate. So this gives us a quick glance view of the system's success rate across multiple time windows. Last hour, day, 7 days, and 28 days. It helps our teams answer the question, are we meeting our SLOs, and is there an ongoing issue? It also gives us a clear temporal granularity. So every tile gives you a summary of the success rate for a defined period. It lets teams spot these short-term anomalies without losing sight of the long-term anomalies at the same time. We also have time series insight to go with it. So the below gives you a visual trend of success rate over time. You can immediately see there's a dip showing when performance briefly dropped. So this makes it easier for us to correlate things like with incidents with our timelines and deployments. Let's take a look at two different examples of burn rate. So there's a side-by-side comparison illustrating why burn rate is such a powerful SLO signal, especially when it's tracked across these multiple time windows that we just talked about. On the left, we're looking at a transient incident. There's a sharp spike in the 1 hour burn rate. Signals that something serious happened, but it was short-lived. The longer time window stayed flat. This suggests that there's no real long-term impact on reliability. However, on the right, for a certain period of time, the burn rate starts low and gradually increases over time between the 1 day and eventually 28-day window. This is a classic persistent issue. Nothing looks critical in the moment, but over time, what will happen is the system is quietly eroding your error budget. So this slow burn often slips under the radar unless you're looking at the burn rate over time. So that's why these windows are so helpful like this. Monitoring multiple windows helps you to distinguish a noisy blip on the left from a real structural reliability issue. Both scenarios have different kinds of risk. One's a fire drill, one's a slow drift, but it goes into an SLO violation. But for each of these, of course, you will have different responses. Let's talk about streaming latency and define a few things. So this diagram helps us to better understand two core latency metrics that are really important for LLM inference: time to first token, TTFT, and inter-token latency. Time to first token is the time it takes from when a prompt is sent to when the model returns its first token. So it includes the tokenization, initial prompt processing, prefill, a decode pass, and finally detokenization. This metric is critical for the perceived responsiveness. So a fast TTFT gives users confidence that the system is working. A slow one creates the impression of lag or that the system is stuck. So for conversational interfaces, it basically defines the first impression. Intertoken latency, ITL, is the time taken to generate each subsequent token after the first. So from the user's perspective, this governs how smoothly the output is streamed, especially for longer completions like documents or summaries. If it's considered inconsistent or slow, the user experiences a jerky delayed output, even if the first token came back quickly. So let's look at some examples of this streaming latency. This slide focuses on the streaming latency, which is very crucial for understanding your real-time responsiveness for Gen AI systems, as we just discussed. So we can see here that the time to first token hovers between 400 to 700 milliseconds. We can say that's fairly standard, but there are some dips and spikes that we also see. These could be linked to things like cold starts, load imbalance, or back in queuing even before the inference starts. Intertoken latency is mostly low and consistent, but there are periodic spikes. What could this mean? Concurrency limits, batching inefficiencies, or degraded transformer performance. Just some things to keep in mind. So together, these two metrics offer a holistic view of our users' perceived latency, and ideally, we want these latencies to be low and stable, not spiky. So this kind of observability is essential for Gen AI systems, but not just for engineers, but also for our product teams, because in Gen AI, performance is the user experience. Now let's talk about throughput. This panel gives us a snapshot of the health and reliability of the predictor gateway based on our HTTP response codes. So this looks great, right? We have over 55,000 total requests, and every single one of them returned to 200, which on the surface looks great and has no user-facing errors. We see 0 400s, no client-side misuses or bad input. There are also 0 503s, no service-side issues. Now, this might seem perfect. In most production environments, as you may know, a true 100 success rate is pretty rare. So it's not that it's not right, but it is a prompt to check a couple of things. Like, are we correctly capturing error responses in our logs and in our dashboard? Are failures being filtered out of our dashboard unintentionally? Are they being retried in our service or overwritten before they actually reach the metrics? All of these things we need to check just to make sure. If everything checks out, then that gives us confidence that the systems perform reliably. But if not, then we might need to visit our instrumentation and logging just to make sure that we're seeing the full picture. So now let's talk a bit more about some throughput. So this chart gives us visibility into how the model is being used over time. It's tracking the token throughput. So it's broken into two different things: prompts and generations. The green line is prompt tokens per second. The yellow is generation tokens. In other words, it's the model's output. So first we see a large spike in prompt traffic early on. It crosses 5,000 tokens per second. What does this mean? Maybe a batch job, maybe a burst, or maybe high demand from upstream services. So following that, we see continued bursts throughout the day, not as high as the initial one, but then we see that traffic gradually tapers off, almost completely drops off. What could this mean? Maybe there's a scheduled shutdown, traffic routing issue, or a scaling event. So just be aware of what also no data means for your workload. If generation suddenly drops or disappears, it could possibly be a sign that something's not working as expected and should be investigated. So another key insight is that generation tokens here consistently stay low, even during periods that have heavy prompting. That could point to short completions compared to the prompt. prompt only operations like embedding or validation steps, or maybe there are also inference failures or timeouts post prompt. It is important to know your service and what you expect so you can correctly evaluate these. And this is giving you some tools just to kind of know what to look for. So this throughput analysis helps us to, correlate these patterns with things like cost, latency, and our error budget. Let's talk about end-to-end performance in this larger overview dashboard. So this gives us a pretty detailed look into our response times across our full predictor spec. We have different components. It's great for platform teams like the gateway. We have a proxy that handles requests coming into inference service and the model itself. So on the left, we see percentile breakdowns of latency. The gateway layer is performing pretty well. It's P50 is sub milliseconds. So our network and routing layers seem good and healthy. But when we shift to the actual model for our inference service, you'll notice that response times are much higher. But that's not actually alarming because it tells us that the bulk of our latency is tied to inference and queuing, which we expect. It shouldn't be on the gateway anyways. So if we look at the middle and right panels, the queuing delays show some spiky behavior, especially around P99, which could suggest intermittent queuing pressure, like bursty load patterns or uneven request batching. These spikes don't actually degrade overall performance significantly, and they're pretty short-lived. So our tail latencies remain within our acceptable bounds. Overall, seems like everything's performing well, but these traceable queuing spikes highlight just an area that we might want to optimize, especially around auto-scaling, load distribution, or queue prioritization. Finally, all response co-latencies are tied to successful 200 responses, which means we're not seeing a latency inflation due to retries or errors, which is exactly what we want. Let's talk about another contextually helpful view, which is capacity and utilization. So this dashboard gives a GPU focus on the resource and demand and usage over a period of time. It combines both real time and historical context so that we can assess how effectively GPU resources are being utilized. So here we see low and sporadic use throughout most of the week, even though request counts were high at times. The actual utilization remained well below 100%, often under 40%, which could indicate a gap between allocated and used resources. So resource utilization is important. It's also a hard problem to tackle sometimes. So this could be due to a few things: inefficient job scheduling, over provisioning, idle allocations, or for people like platform teams and end users, it could be an optimization opportunity. So at the workload or the scheduling level. So let's talk about tracing and how it helps us just to understand our metrics a bit. Here we see a trace where we are just under 700 milliseconds from start to finish. We can see the different components here. So all operations here are within a single service, test service, but they span multiple internal steps. So there's a few steps here that are comparatively lightweight to our inference requests, which span actually dominates the timeline. It accounts for the majority of the total latency, and this is exactly what we expect in AI workloads. So inference is definitely the heaviest step, right? We often see this as the source of our bottlenecks or our SLO violations. But this trace is helpful not just for debugging slow requests, but also for understanding where you should or shouldn't invest optimization effort. Now that we defined our SLOs and we've created our dashboards and we have all the data, let's talk about making them actually actionable. That's where we use our burn rate to configure alerting comes in. So a burn rate tells us how quickly we're consuming our error budget. When the burn rate's too high, it's a sign that the system is degrading faster than our SLO allows. So let's break this down quickly. So 1 hour burn rate above 13.4. So you're burning your entire budget for a 30-day period in just 2 hours. So this is a major outage, right? You want a high priority alert here. A 1-day burn rate above something around 2.8, it's not great, but it could mean a moderate issue it's just not immediately catastrophic probably, but it could escalate quickly. So if you have a 7 or 1-day burn rate that exceeds 1, this is something that you're seeing a slow burn over time build. It's less urgent. It might be a sign of an ongoing issue or something that you want to look at and optimize or fix. So what the key is to match these thresholds to your environment. Don't treat dev and prod the same. You want to surface your high severity issues quickly in production, but you don't want to drown in noise elsewhere. Don't just fire alert on every blip. You want to focus on things that are specific, meaningful, sustained violations, prioritize based on severity and impact. And remember that alerting's not static. You'll need to tune it over time. You need to use incident retros, postmortems, and SLO reviews to refine your threshold. So this system, let's take a look about how to refine, and I'll try to go through these very quickly. So we're going to look at two different ones, and then we'll wrap it up. This system's likely dealing with a persistent failure mode. So here we see something like a misbehaving deployment or bad handling of edge cases or something like that. The burn rate is high across every one of the windows. This isn't just a spike. It suggests that an issue has been ongoing and it's not been mitigated. At 10.3, it's burning through its entire allowable budget 10 times faster than tolerated. So it's critical, it's unsustainable. So all windows show negative budget. We're in like the whole non-compliant territory. Above, you see scattered dips in the success rate. Type of change, or you need to adjust your SLOs because they're just not realistic. Let's take a look at the opposite, but another scenario. So in a production system, as we talked about, this might be a little bit suspicious, right? Because it's almost too good to be true, possibly. So it suggests either that the metrics aren't being recorded accurately, which I think for this one is true. If you see that they're, if you see the bottom left one, that kind of doesn't make sense. And it could mean that also the errors are being swallowed or misclassified. Maybe in your dashboard rule, you like filtered it wrong. So next you need to just take a look at how your error budget is being used. So if you're not using it at all, your SLO might be a bit too relaxed. And on the flip side, the last one, you might be burning through it constantly. You might be too aggressive or misaligned. So patterns in burn rate could tell you a lot. Maybe a certain type of error is more common during the batch traffic or latency spikes. You need to use this data to fine-tune your SLOs. But just remember that every incident is a learning opportunity. If you had downtime and that didn't register as a violation, that's a sign that your metrics or thresholds might also not be measuring the right thing. So just to wrap things up, if you're building or running an AI platform, observability isn't optional, it's foundational. So we've seen how we use our observability stack using our Gen AI platform as an example. We built it with a lot of open source tools like OpenTelemetry, Grafana, Envoy, Prometheus, Kserve. So these things really help to give you full visibility across pipelines, layers, and GPU usage. But tooling alone isn't enough. Make sure that you have best practices, and most importantly, observability is never done. So the most resilient platforms are the ones where feedback on these incidents and data is a constant feedback loop that helps you to refine your improvement. So if you walk away with one idea from today, let it be treat observability as a product, not just a tool set, and build it to evolve as your platform grows. So we are hiring. Check this out. I'll try to post these somewhere. And thank you for joining us on our quest, and the campaign continues.
Awesome. Thank you so much for that. And I think there's one or maybe a few questions.
There's definitely a few questions. So if you want to